Mr. Eric, Mr. Ryan, alright? Hello, hi, Eric. So we have talked about the longest trees. Remember a few days ago, yeah? Longest path in a tree, in a binary tree. What's binary tree? What's binary tree?
Binary tree is a binary tree, right?
It's a tree. This is the root, yeah, growing downwards. These are the leaves, yeah. Okay. So we want to find out the longest path. Longest path is the path between any two nodes. So what's the longest path here? Right? How many nodes are in the longest path? Anybody? What's the longest path here? Let's say I put another node here. What's the longest path?
4.
4 or 5, yeah? Right? 2, 1, 3,
7.
8. Okay. Yeah. We talk about the depth search, yeah? Depth search. The function, remember the function returns two things. DFS root. The first of all, this function returns the number of the nodes, the longest path, starting with the node, right? And the function also stores the maximum, the longest path between any two nodes because we're passing the root, right? Right? Let's quickly review this, yeah? If no root, return 0, yeah? Return 0 because if it's empty, the longest path is 0. Okay, so left equals DFS root dot left. Right equals DFS root dot right, okay? And then, okay, so we have an answer here. At the beginning is 0. Answer equals maximum answer.
Take no sugar.
Okay. So look, here we are root. At this point we are root here, right? Sorry. DFS root dot left is this bit. It's this bit. The longest path is this bit. Yeah? Passing the root dot left. DFS root dot right is the longest path, passing the root dot right, which is 3. Okay, so here is L, here is R. Okay? So now the longest path passing the root here, 1, is equals to what? Is equals to what?
Equals to
L plus 1 plus R. So here. Right? But now this function will return the longest path starting from the root. Right? So it means that either the left or the right, we want to pick the maximum, right? Alright? So return maximum. When we talk about this, yeah? L, R plus 1, right? Okay? Look, alright. These and this a little bit different, right? This is the two things this function does. The recursive depth search. Okay? Okay, now look, this tree. What are trees? Binary tree. DAG. What's DAG, by the way? Anybody remember? What's DAG? Acronym for?
directed acyclic graph.
Well done. Directed. Directed means there's a arrow, yeah?
DAG.
Arrows are from the parent to the kids in the binary tree, yeah?
Yeah.
Yeah, because the binary tree, the trees are usually you visit the children from the parents, right? Let's call it directed. And acyclic, what does it mean? Acyclic. Acyclic. Does it? What's the acyclic mean? Anybody?
Acyclic means that it goes around in a circle.
But
and then it stops.
Acyclic. Means the opposite. Means doesn't have a cycle.
It
Yeah.
doesn't say
Acyclic. Okay. The graph is basically a collection of the vertex and
said the opposite.
okay, vertex and edges. Yeah.
See, that's logic.
Okay. Vertex. Okay. Can I see your face, please? Wait.
My face is a Pikachu.
Okay. So now.
You see, Pikachu.
Alright. We also talk about converting the trees into a graph, right? We also talk about what's the advantage of converting the trees into a graph. Anybody? Why do we need to convert the trees into a graph?
Because it's much easier.
Much easier in sense of what? In sense of what? Much easier in sense of what?
In sense of.
Look, as a trees, we can only visit the children from the parents, right? But if we converting the trees into the graph, then we can visit the parents from the kids, right? So because when we convert the trees into a graph, we are converting into a unidirectional, bidirectional graph, right? So it means two-dimensional, bidirectional graph, okay? Bidirectional graph, right? So like we can use the depth search or breadth search. Usually we use the depth search. We're passing through the root and the parent, right? And then we can store the graph in an adjacent list from the parents to the kids and from the kids to the parents, right? Okay, so today, look, listen up. This is the key point today, okay? Right? What's the longest, the furthest node I can travel from the root here, from the root 1? What's the longest?
The right.
Which number is it?
4.
What's the longest path I can travel from here? If I walk here, if I use the breadth search, yeah, what's the longest path I can travel to? Which node? What's the longest point from? If I start from 8, okay. Then I go here. Okay, now what's the longest point if I start here? I can go. You know, visualizing this as a graph. What's the longest point if I can travel from here?
1.
What 1? Imagine this is a graph.
Yeah.
This is a graph. Why, if 1, why can't I go further?
Because.
Don't worry. Look, this is the graph. If I'm here, I'm doing a breadth search. I'm here. And what's the longest place I can be? What's the longest path I can be?
7. No, 3.
So, why is it 3? Yeah? No, the longest path. Don't worry about the arrows because it's a two-directional now. It's a graph now. I'm here. What's the longest place I can be?
4.
4. Okay. Yeah. Okay, so I'm here. So this is the longest path in the graph. It makes sense? Okay, so how about here? Okay, this works. So what did I just do? I start with any node, right? I do a depth search or breadth search to go to the furthest point I can be, right? And then I do another depth search or breadth search and find another node. And these two are the longest. The paths between these two nodes are the longest. Okay, so let's give another example. Okay, let's give another example. Okay, so let here let's say we start from this place. Yeah, what's the longest path it can be?
The really bottom.
This one, yeah. Okay.
Yeah.
Okay, I'm here. What's the longest path I can be?
The really top left.
Okay. So the longest path will be the root between these two. Okay? Yeah? Make sense? Make sense?
Yeah.
Why this approach is working? Why look why this is working? Can you find any other example that this approach doesn't work? So the point of doing that is that doing two depth search is that we can allow this, you know, going out of a global local optimum, right? Yeah. So let's find maybe another example, okay? Maybe another example. So I'm here. I'm here. So this is the local minimum here. And now I have something going round and round and round. Okay?
In a circle.
Yeah, maybe. Let's say. But it should be a graph, right? It should be no cycle because if it says it's a cycle, there's no longest path. You can, if there's a cycle, what's the longest path?
Nothing.
What's the longest path of this one?
Infinity.
Infinity. Where down? Look, if it, because I can just go through round and round and round, right? It's if it's a circle, right? Yeah. Can I have your attention? No too much noise, please. Okay, so I'm trying to find out the example that you tell us why this approach works. If we pick any node and we do the longest depth search, longest path, then it will work. So maybe this is too obvious, yeah, because any node will pick this longest one, right? So maybe this is not a very good idea. So
Woohoo! Looks like a guy who has long hair.
yeah. Okay, so look, if we start from here, what?
So funny.
Look.
And now he has an armrest.
Yeah, look, if we pick a node which is not the terminal node, right? Because usually the terminal node, Eric, right? If we pick a node in the middle,
Yeah.
that is not the longest path, right? If they look, because we pick here, now what's the longest path? You come to this point here. Yeah, and then we can go through here again. The longest path will be okay. So here, right? Yeah. So look. What's right? Look, what's the why this is working? Okay, maybe I will do this. Okay, here, one more node here. So look, I start from here, the longest path.
The top one.
Okay, you will pick this one. You
Pick
pick
this
one.
one.
Okay, I'm trying to pick another one here. Look, which is here. Okay, look, the longest path. I start here. You pick this one, right?
Why?
Look, because from here you go here. There are odd. So 1, 2, 3, 4. 1, 2, 3, 4. Okay, I have another one. Yeah.
Okay, that's
Okay, so
why
then
I said why.
we're done. I'm here, right? This
Thank
one.
you very much.
Right, and then from here you go to here, right? Yes. Yeah. Look.
Oh,
So you see. So the first depth search, you allow the node to jump out, right? To find this, find the furthest point from here, and then from this you can see more area, right? We go from here to, and you will pick the path. Okay? Okay? Make sense? Okay, so can you tell me what's the approach here? How can we find the longest path?
It's because we always that says grape, not graph.
Yeah? Graph. What's
That says grape.
where's the grape? Oh, graph. Okay. Directed graph.
Directed acyclic grape.
Can you tell me what did I just say here?
And there's no E at the end. That the longest path is when you pick a random node, you always like to choose the one that has the most.
Yeah. It's not easy to prove, right? But it's by intuitive is that you pick a random node, you do a depth search to the longest path, yeah.
You always get the actual answer's length up.
Yeah, and then you start here, you do another one, right? Okay, so then you help us to find the longest, right? You help us long path. You see, you get the meaning, yeah? Do you understand?
Yeah.
Okay, maybe I try another one, and then you tell me, okay? I just draw anyone, and then you tell me what's the longest path. I don't know, okay? I'm just guessing. Okay, what's the longest path here? Can you try any? Can you?
Left 1, 2, 3, 4, 5.
Okay, so
6. 1, 2, 3, 4, 5, 6, 7, I guess.
7. Okay, so let's say if I start from here, right? What's the longest path you can go?
The top
Right.
sizzle one.
Yeah, okay, here. And then here, I can go from here, right?
Yeah.
So 1, 2, 3, 4, 5, 6, 7. We're done. Okay? Yeah? So you found it, yeah?
Baby.
Okay, so this is a simple strategy. Yeah, so look, we can do this breadth search. We can breadth search on this bit, okay? We can breadth search on this bit.
Left is triangle.
Okay, let's write this, okay? Let's write this. Let me remove this bit, okay? Because we already seen this code before. And here. So first of all, we want to convert the graph into, convert the binary tree into the graph, right? Okay, so let's say G equals default dictionary, okay? We use this default dictionary list. This is the node, right? And then we can do this DFS by passing the root and the parent. Why do we need to pass the parent here? If not root, return. Can you tell me? I'm trying to convert the tree into the graph and I'm passing the parent. Okay? Return. Okay? And then we can say DFS root dot left. What's the parent of root dot left?
Root.
And then I'm trying to DFS root dot right. What?
Root. Like some baby.
Okay, now if parent is set,
So funny.
so look,
Like
root,
saying other.
the parent of root is parent, right? Look, the parent of root is par, okay? Yeah. So now we have par, then we want to construct the edge between the parent and the root, right? So if a parent,
You
then
just
we
call
can say
it par, and then you call it parent.
like G parent is dot append root, right?
He called it parent.
And then G, I want to append another edge, which is what?
Subject.
Come on, I'm adding an edge between.
Par.
I'm adding an edge between par to root, and what's the next thing? I want to add another edge the reverse way. So what should I do?
Root to par.
Yeah, root dot append, right?
Root to par. Tay.
Okay. So this one converting the trees to the graph. Okay. We use the G default dictionary. The key is the node. The value is the list of the vertex nodes. Yeah, it connects to. Make sense? Yeah. Okay. The time complexity for this one. What's the time complexity if we try to convert the trees into graph? What's the time complexity?
Oh, no.
Oh, n, because there are n nodes, yeah, n nodes, and then that will be mapped to n vertex. Okay. What did Daddy just say?
You said, we can use the partridge in the pear tree.
Okay. The time complexity and space complexity is both O(n) because we are visiting the n nodes in the tree and we're converting the nodes into a vertex. In the binary tree we call it nodes. In the graph we call it vertex. Okay, vertex. Edges. We are having two edges. Parent to root, root to parent. Okay, both way, two directional. Oh now, okay, so now once we have this graph ready, then we need to do this breadth search. When we have this breadth search, or we can do it depth search, it doesn't matter, right? We start with the root, right? Right? And then we want these functions to return the furthest point from root and the distance. Yeah, make sense? Look, remember this, yeah? We start with any node. This could be root node, every node, right? And then you tell me the furthest point is here. Yeah, you return a tuple. The first value is the furthest point. The second value is the distance to it. So that will be 1, 2, 3, 4, 5, 6. Make sense? So this function will tell me that. Right? And how does that useful? Look, if this function return that, and what should I do? Look, alright. Come on, this. Okay, don't worry about the implementation. About this one is root, right? This is root. Right? And then this function will return to a tuple. So I can do this. Look, the furthest point, furthest, F-U-R-T-H, furthest, and the distance equals BFS root, right? And then you tell me is this bit. Okay, the furthest, then we'll go to this bit, yeah? This is the furthest. You tell me furthest. And the distance will be 1, 2, 3, 4, 5, 6, 6. Okay, and then what's the next thing? What's the next thing I should do? What's the next thing? I got this value. What's the next thing?
You should
Do another what?
do another depth.
breadth search. And then I need to do this one. Look, BFS furthest. Okay? Look, I do the furthest. And then return to value, which is another one, I don't care, underscore. I don't care. And then that will be the distance. And I just need to return the distance. Okay? Because after this, you will tell me the furthest point is here. This is another one. Let's say A. Okay? Here is A. And here is A. Okay? Then distance will be 1, 2, 3, 4, 5, 6, 7, 8. Okay? Distance will be A. Do you get it? I'm calling this a breadth search twice. Yeah? Make sense?
Okay.
What did I just say? Can you explain to me?
Breadth search twice.
Breadth search twice. This breadth search can be replaced by depth search, okay? But we're using breadth search. Sorry?
Nothing.
Okay.
Oh,
Okay, so now the breadth search. Okay, so then let's implement breadth search. How can we implement the breadth search? There's one data structure we need to use, which is what?
Q.
Q. I know.
DQ.
Yeah, Q equals DQ. And then let's. At the beginning, we need to put the root, and then the number of nodes is 1 here. It's a tuple. And we want to find because in the graph we need another data structure to find out if we have visited the nodes before, and what kind of data structure would that be? The thing that asks to check if we have visited a node before. What would that be? Notebook, a hash set. Okay, scene equals hash set or set. And then let's say answer equals the. Okay, so then the furthest. Let's say the furthest. Let's just call it furthest equals root, and distance equals 1. Okay, 1 node. It's actually not the distance, it's the number of nodes. Okay, and then we can say while Q and current D equals Q dot pop left. Okay, and then we want to find out, look, if D bigger than the distance, the number of nodes, then distance equals D. And furthest, we store the furthest point at this point, and which is current. And then let's say we want to find out the nodes it connects to. So it will be for n in G current. If n not in scene, okay, not in scene dot add n, and then we want to push this append this to the Q. So Q dot append what? Append the next node is n, and the distance, the number of nodes increase will be d plus 1, right? Okay, and then later we return a tuple, furthest, and then distance. Okay, you see? Breadth search, yeah? A breadth search. Okay, so what have you learned so far today?
About the longest path.
Longest path, breadth search. Yeah.
Yeah.
We can use the
Yeah.
we can use the depth search here as well, right? Even we can use the depth search to breadth search. Look, at the beginning we use the depth search to convert the trees into the graph. We can use the breadth search at the point as well, right? Yeah. We are using breadth search to travel to do this traverse to the longest path, to the longest point from the loop, from the current node, right? We can also use depth search to do it. The key points today is that how do you find the longest path? Yeah. We start with any node. We can go to the furthest point from here, and then we start at a point to do another, traverse. Yeah, we can do the depth search or breadth search from that point. Yeah, remember this graph. Yeah, the time complexity is O(n). Breadth search, we do it twice. It's O(n). We drop the constant, which is O(n). Right? The space complexity obviously O(n). Right? We need a hash set notebook to store the number of nodes. We have theme. Yeah, we are converting the trees into the graph. We also need the data structure to store the graph, right? Graph, vertex, and the edges. Okay, so look, the number of vertex is n. The number of edges is what? The number of edges. If a tree has 3 nodes, what's the number of the edges? The maximum edges. Okay, the one last question. If a binary tree has n nodes, how many edges are there? the maximum. There are 1, 2, 3, 4, 5, 6,
N
7.
minus 1.
So it's a magnitude of n, right? Something like that. Look, because it doesn't have cycle. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Yeah, okay, you're right. Okay, look, and if I 9 on the 1, 2, 3, 4, 5, 6, 7, 8. 8 edges. How many nodes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Yeah? You know why is that? Why is that? I'm a tree. A tree with n nodes has n minus 1 edges. Am I right? Yes? Why is that? Look, consider this one. 3 nodes. N minus 1 edges. Alright, look. Why is it n minus 1? If I add in one more, what happened? Look, n nodes. I'm adding, if there are n nodes here. N minus 1 edges. If I add in 1 edges, what happened? Cycle. There will be cycle. Okay, so VE is also n, right? We're storing the nodes and the graph. Okay? Okay? Everyone, okay, so can you tell me what have you learned so far today? The last question, please. And that will be it.
Research.
What's the problem we're trying to solve here?
Longest path.
Longest path. And how are we doing it?
By picking a random number.
Random node. And then?
And then research.
And then?
Then research again.
Okay, we're done. Good job. That's it for today. Good job. Bye-bye.
Bye.
Bye-bye. Do a little bit dancing, please. Bye-bye.
Bye. Bye.
Come on, come on, come on. Come on.
Bye.
More upbeat.
Bye.
Okay, that's it for today. Bye-bye.
Bye.